In this video, we are going to talk about pulleys and constraints using this simple pulley problem that you've seen a whole bunch of times as a launching point to talk about them. We want to find a systematic way to think about constraints so that way you can solve more complicated problems, especially with pulleys. All right, so as usual, you can create a free body diagram for these pulleys, and I've already done it for you. But this time what I'm going to do is I'm not going to call it T. I'm going to call the tension T1 and T2. And likewise with the acceleration of my masses, I'm going to write them as A1 and A2. And then what I'm going to do, which is different, is I'm going to explicitly draw a global coordinate system. All right? So I have up as positive and to the right as positive. And then have my origin centered on the center of the pulley. If I do that, I can use Newton's second law to now write out my equations. If I write the x direction for m1, I could write the y direction, but I don't care about it for this problem. If I write out the x direction for Newton's second law, I get t1 is equal to m1, a1. And then for m2, I only really care about the y direction. I don't care about the x direction, so I'll just write out the y direction. There isn't really an x direction anyway, no forces and no accelerations. So in the y direction, according to my global coordinate system now, up is the positive direction. So I have to write T2 minus M2G equals M2 A2. And now I am going to write my constraint equations. So one of them is, because we have just one rope connecting both of our pulleys together, one of them is that a massless rope has the same tension all the way throughout the rope, assuming it's not getting stretched or compressed or whatever. So I have that T1 is equal to T2. The tension in the rope pulling M1 is the same as the tension in the rope pulling M2. Let's just call that T. But now let's think about the accelerations. So the acceleration for A1 is going to have the same magnitude as the acceleration for A2. However, A1 is in the positive direction according to my coordinate system, whereas A2 is in the negative direction according to my coordinate system. So they'll have the same magnitudes, but they'll have different directions. Or another way to write that is that I can make my acceleration of A1A and therefore my acceleration of A2 minus A. These are my constraint equations. I can then take my constraint equations and plug them into my Newton's second law equation. So for x direction here, I plug it in. I get T is equal to M1A. Then over here, I plug in and I get T minus M2G is equal to M2 minus A, which I can divide by minus 1 on both sides. So then I arrive at the same equation you're used to seeing for these pulleys. We have the same equations of motion as we did with solving this pulley the usual way, and so we will have the same solution. We have the same system of equations, so we'll have the same solution to them. That was finding the direction of this in a somewhat intuitive way, right? We just looked at the directions of positive and negative. But now I want to think of another way to get the acceleration constraint that will generalize to more difficult pulley problems. So the constraint that we're going to have is we're going to recognize that the length of this rope stays the same because it's not getting bunched up on the pulley, it's just moving over the pulley. So the length of the rope is constant throughout the entire motion. And then what we're going to do is we're going to write coordinate functions for M1 and M2 according to the origin. So M1 is at position, let's call it X1, and it's changing with time. M2 is at position, let's call it Y2 to match the mass there, and it's changing as a function of time. Let's now write the length of the rope in terms of these coordinate functions. Notice X1, because it's to the left of the origin, is always going to be negative. So if we want the length of this line right here, which as you can see, the length of that line is just one part of the length of the rope from here to here. If we want the length of that line, we need to write minus x1. So we have minus x1 of t. Then similarly, the length of the rope from here to here is going to be minus y2 because y2 is going to be negative. So we want a positive value for length, so you make minus y2. And then finally, there's a part of the rope that's just hanging around the pulley, curling around it, right? That part of the rope is always constant because the rope just flows over the pulley and then comes down, right? So let's call the length of that rope, let's call it C. So it's just a constant value of rope that's just bending over the pulley. So this means at any moment in time, the length of my rope can be written like this. All right, now what we're going to do is we're going to use calculus to derive acceleration constraints. So if I take the time derivative on both sides of this equation, well, ddt of a constant, that's going to be 0. And likewise, if I take ddt on this side, the c is going to go away to 0. And so, as a result, taking the time derivative of both sides, we get time derivative of minus x1 of t minus time derivative of y2 of t, and then plus 0 because of the c there. Well, what's the time derivative of position? The time derivative of position is velocity. So we get minus v1 of t minus v2 of t. As a side note, point of notation, sometimes people write time derivatives of functions using a dot. So they might write this like this, where one dot means one time derivative of x. And then if they do a second time derivative, they'll use two dots. So in case you look at other videos, you know what that means. But anyway, continuing on. All right, so now we have velocity. Let's take another time derivative of both sides of our equation. So time derivative of 0 is 0. And then, as you know, the time derivative of velocity, say v1, for example, that's just going to be acceleration. So we get minus a1 of t minus a2 of t. We can then add either of these to the other side to get a relationship between a1 and a2, and we see that a1 is equal to minus a2, which is indeed the constraint that we had earlier. So this is how you can get the constraint in a systematic way. You create position functions for your masses. You remember that the total length of your string is constant, and then write the total length of your string in terms of those position functions. We sometimes call them coordinate functions. Then you'll always have this little constant part, which is going to go away when you take a time derivative anyway, which is wrapping around the pulley and never changes with time. Then you take two time derivatives of both sides, and that will give you your acceleration constraint that you can then plug into Newton's second law that you derived.